Today, let's dive into a mysterious and fascinating realm, the wondrous world of infinity. Imagine standing on a boundless prairie, with the horizon stretching endlessly before your eyes. Doesn't that sense of infinity leave you both awestruck and puzzled? The mathematical concept of infinity is like that prairie, vast and elusive, beyond our grasp. But don't worry, mathematicians have already equipped themselves for this exploration, delving into this imaginative domain and discovering that infinity differs vastly from the numbers we encounter in daily life. When it comes to explorers of infinity, we must mention the German mathematical prodigy, Cantor. He posed a perplexing puzzle. Imagine you have an endless supply of candies, integers, like 1, 2, 3, 100, while your friend has a line filled with countless points. So, which is more numerous, your candies or the points on that line? This question might sound like a child's game of comparing toys, but mathematicians take it seriously. Their method of comparing infinities resembles a game of matching pairs with a friend, seeing who can find more unmatched items. Imagine you and a friend each taking out a pile of coins and starting to match them one by one, seeing who has coins left over at the end. Although this sounds somewhat childish, this is precisely the approach mathematicians use when comparing two infinities. For instance, both odd numbers, 1, 3, 5, and even numbers, 2, 4, 6, are infinite. You can pair odd number 1 with even number 2, odd number 3 with even number 4, and so on. You'll find that odd and even numbers are like perfect dance partners, always finding a corresponding other half, so their quantities are equal. Even more astonishingly, the quantity of integers, including all odd and even numbers, is equal to the quantity of even numbers. It's like saying that all your candies, integers, are as numerous as your friend's even-numbered candies. This sounds like magic, where a part equals the whole. Speaking of magic, we cannot overlook the famous Hilbert's Hotel thought experiment. In this hotel, the number of rooms is infinite, and no matter how many guests you add, even infinitely many guests, the hotel always has empty rooms. So, does infinity multiplied by infinity still equal infinity? Let's make an interesting comparison. Which are there more of, integers or rational numbers? Rational numbers include integers, finite decimals, and repeating decimals, making it seem like there are far more rational numbers. However, mathematicians once again play the matching pairs game and find that a one-to-one correspondence can also be established between integers and rational numbers. We know that rational numbers can be expressed in the form of p divided by q, where p and q are integers, and q is not zero. We can list all rational numbers in an infinite table, with the horizontal axis representing all integers p and the vertical axis representing all q. So, all rational numbers represent an infinity multiplied by infinity scenario. Then, how do we establish a one-to-one correspondence between integers and all rational numbers? By looking at this table of all rational numbers, we start from the top left corner and keep drawing squares, with each node corresponding to an integer, thus establishing a one-to-one correspondence between all integers and rational numbers. Through this example, we find that all rational numbers are as numerous as integers. In the world of infinity, the whole can be equal to the part, and addition and multiplication lose their meaning in the everyday world. We refer to this level of infinity for integers as Aleph 0, the smallest level of infinity. In the context of infinity, the whole and the part can indeed be the same. Infinity plus infinity equals infinity, and infinity multiplied by infinity still equals infinity. Our everyday mathematical concepts break down here. However, this is not the whole story of infinity. The number of points on a straight line is much greater than Aleph 0. We can imagine this line as a unit-length straight line, with the points on it representing all real numbers between 0 and 1. As we know, all real numbers include rational and irrational numbers, and irrational numbers, like square root 2, square root 3, etc., that do not repeat infinitely cannot be matched one-to-one with rational numbers. Therefore, all real numbers represent a higher level of infinity than all rational numbers, called Aleph 1. Are the numbers of points on two line segments of different lengths the same? In fact, they are. If we place these two line segments in parallel and connect their ends, forming a triangle, and then draw a line from the top of the triangle intersecting these two line segments, we'll find a one-to-one correspondence between the points on the line segments of different lengths. Moreover, not only do line segments of different lengths have the same number of points, but lines, and planes, and even cubes, have the same number of points. This is another intuition-defying fact. Taking a line and a plane as an example, assume a point on the plane has coordinates 0.a1, a2, a3. 0.b1, b2, b3, on the horizontal and vertical axes, respectively. Then, on the line, we can find a point 0.a1, b1, a2, b2, a3, b3. That corresponds to it one-to-one. The same applies to cubes, just with an additional parameter c. Therefore, the number of points on real numbers, lines, and cubes all belong to the second level of infinity, namely Aleph 1. So, how many levels of infinity are there? Currently, we have discovered 3 levels of infinity in life. The first level of infinity is the number of integers. The second level of infinity is the number of points in geometric structures like line segments, rectangles, and cubes. The third level of infinity is the number of all curved shapes. This might sound abstract, but it means that we can draw infinitely many shapes of curves casually, and the total number of these curves is infinite, belonging to the third level of infinity and representing the largest infinity discovered in daily life, denoted as Aleph 2. Will we discover even higher levels of infinity in the future? This remains an unknown question.